Converting cable impedance to per unit impedance is a crucial step in power system analysis and simulation. Your approach to converting the cable impedance to per unit values for a 1000 foot length is indeed accurate. The base impedance, Z base, is calculated using the formula Z base equals the square of the voltage divided by the system MVA. In your case, with a 600 volt system and a 10 MVA base, Z base equals 600 squared divided by 10 times 10 to the power of 6, which equals 0.36 ohms. To find the per unit impedance, CPU, you divide the actual impedance, Z-actual, by the base impedance, Z base. Using the positive and negative sequence impedance value of 0.340 plus J0.79 ohms per 1000 feet, the per unit impedance calculation would be CPU equals 0.340 plus J0.79 divided by 0.36, resulting in 0.944 plus J2.194 per unit. When dealing with different run lengths, you can scale the impedance proportionally. If you have a run length of L feet, the actual impedance for that length can be calculated using the formulas actual per L feet equals actual per 1000 feet multiplied by L divided by 1000. For instance, if you have a 2000 foot run, the actual impedance would be 0.944 plus J2.194. The per unit impedance per 1000 feet multiplied by 2000 divided by 1000, which equals 1.888 plus J4.388 per unit. It's important to remember that the impedance values you're using are based on a specific cable spacing, in your case, 8 inches. If the actual cable spacing in your simulation varies significantly from this value, you should adjust the impedance values accordingly. The spacing between cables influences the inductance and therefore the impedance. Larger spacing typically results in higher inductance. To summarize the conversion, firstly, calculate the base impedance using the system voltage and MVA base. Secondly, divide the actual impedance by the base impedance to obtain the per unit impedance. And thirdly, adjust the impedance proportionally for different cable run lengths. Always consider the impact of cable spacing on impedance, especially when the actual spacing differs from the assumed spacing in the provided data. Now let's delve deeper into the nuances of per unit impedance and its application to different cable configurations and scenarios. The per unit system simplifies power system analysis by normalizing voltage, current, and impedance values to a common base. This eliminates the need to refer quantities to different voltage levels in a system, making calculations easier and more intuitive. When selecting a base MVA and voltage, it is important to choose values that are representative of the system being analyzed. Typically, the base MVA is chosen to be a convenient round number, such as 10 MVA or 100 MVA, while the base voltage is chosen to be the nominal voltage of the system. Once the base MVA and voltage are selected, the base impedance can be calculated using the formula Z base equals V base squared divided by S base, where V base is the base voltage in volts and S base is the base MVA in volt amperes. The per unit impedance of a component is then calculated by dividing the actual impedance of the component by the base impedance. For example, if a cable has an impedance of 0.1 ohms and the base impedance is 1 ohm, then the per unit impedance of the cable is 0.1 per unit. Per unit values are dimensionless, which means that they are independent of the units used to measure the actual values. This makes it easy to compare the impedances of different components in a system, even if they are measured in different units. When analyzing power systems with multiple voltage levels, it is necessary to refer all impedances to a common base. This can be done by using the following formula: CPU new equals CPU old multiplied by V base old divided by V base new squared multiplied by S base new divided by S base old, where CPU new is the per unit impedance referred to the new base, CPU old is the per unit impedance referred to the old base, V base old is the old base voltage, V base new is the new base voltage, S base new is the new base MVA, and S base old is the old base MVA. Cable spacing significantly affects the inductance of the cable. The closer the cables are spaced, the lower the inductance, and the further apart the cables are spaced, the higher the inductance. This is because the magnetic field produced by one cable interacts with the magnetic field produced by the other cables. When the cables are close together, the magnetic fields tend to cancel each other out, reducing the overall inductance. When the cables are far apart, the magnetic fields do not cancel each other out as much, resulting in a higher overall inductance. The inductance of a cable can be calculated using the following formula: L equals mu0 divided by 2 pi multiplied by Ln d divided by R, where L is the inductance in henries per meter, mu0 is the permeability of free space, d is the distance between the cables, and R is the radius of the cables. The impedance of a cable is given by Z equals R plus J omega L, where Z is the impedance in ohms, R is the resistance in ohms, omega is the angular frequency in radians per second, and L is the inductance in henries. The resistance of a cable depends on the material of the cable, the cross-sectional area of the cable, and the temperature of the cable. The inductance of a cable depends on the geometry of the cable and the spacing between the cables. In addition to cable spacing, other factors can affect the impedance of a cable, such as the presence of nearby metallic objects, the type of insulation used, and the frequency of the current flowing through the cable. When modeling cables in power system simulations, it is important to accurately represent the impedance of the cable, taking into account all of these factors. This will ensure that the simulation results are accurate and reliable. When dealing with bundled conductors, the calculation of inductance and impedance becomes more complex. Bundled conductors are used to increase the current carrying capacity of a transmission line and to reduce the effects of corona discharge. The inductance of a bundled conductor is lower than the inductance of a single conductor with the same cross-sectional area. This is because the magnetic fields produced by the individual conductors in the bundle tend to cancel each other out. The impedance of a bundled conductor can be calculated using specialized software or by using approximations. When modeling bundled conductors in power system simulations, it is important to accurately represent the geometry of the bundle and the spacing between the conductors. Transposition is another technique used to reduce the effects of inductance on transmission lines. Transposition involves periodically swapping the positions of the conductors in a transmission line. This ensures that each conductor spends an equal amount of time in each position, which reduces the overall inductance of the line. The length of each transposition section is typically chosen to be a fraction of the wavelength of the power frequency. When modeling transposed transmission lines in power system simulations, it is important to accurately represent the transposition scheme. The ground return path can also affect the impedance of a transmission line. The ground return path is the path that the current takes to return to the source. The impedance of the ground return path depends on the conductivity of the soil and the depth of the ground wire. When modeling transmission lines with ground return, it is important to accurately represent the ground impedance. Skin effect is a phenomenon that causes the current to flow primarily on the surface of a conductor at high frequencies. This increases the effective resistance of the conductor and reduces the effective inductance of the conductor. The skin effect becomes more pronounced as the frequency increases and as the conductor diameter increases. When modeling conductors at high frequencies, it is important to take the skin effect into account. Proximity effect is a phenomenon that causes the current to flow unevenly in conductors that are close to each other. This increases the effective resistance of the conductors and reduces the effective inductance of the conductors. The proximity effect becomes more pronounced as the frequency increases and as the spacing between the conductors decreases. When modeling conductors that are close to each other, it is important to take the proximity effect into account. Harmonic currents can also affect the impedance of a cable or transmission line. Harmonic currents are currents that have frequencies that are multiples of the power frequency. Harmonic currents can cause increased heating, voltage distortion, and equipment malfunction. When modeling cables or transmission lines that carry harmonic currents, it is important to take the effects of harmonic currents into account. Temperature affects the resistance of a conductor. As the temperature of a conductor increases, its resistance also increases. This is because the increased temperature causes the atoms in the conductor to vibrate more, which impedes the flow of electrons. The temperature coefficient of resistance is a measure of how much the resistance of a conductor changes per degree Celsius. The temperature coefficient of resistance depends on the material of the conductor. When modeling conductors at different temperatures, it is important to take the temperature coefficient of resistance into account. Aging can also affect the impedance of a cable or transmission line. Over time, the insulation of a cable or transmission line can degrade, which can lead to increased leakage current and decreased insulation resistance. The conductors of a cable or transmission line can also corrode over time, which can increase their resistance. When modeling aged cables or transmission lines, it is important to take the effects of aging into account. The accuracy of your impedance data is crucial for accurate simulation results. Always verify the source and validity of your data and consider the factors discussed to ensure your model accurately reflects the real-world system. By understanding these factors and their impact on cable impedance, you can create more accurate and reliable power system models.